This is a video about battery management systems, or BMS for short. Now in another video I'd taken apart a solar generator and it had a battery pack just pretty much the same as this. And a battery management system is something that most products these days that have any kind of lithium-ion cell in it, they're going to have some kind of battery management system in there. And that's for safety reasons, but it also helps ensure that the batteries give the expected cycle lifetime. The expected cycle lifetime means that each cell can only be charged or discharged so many times before it basically is not useful. Or it may be until it loses 80% or 20% of its capacity, or it depends. There's different ways of looking at it. So this pack is very typical. It has 18650 cells and they're all spot welded together in a factory. That may be a human or automated process. It very commonly is done by humans and not by robots. It's a lot of work, but it's less work than soldering the cells. But the main part of this video is going to be this board on top. So I'm going to try to raise this up closer to the camera where you get a better view of it, so we can look at the board. Okay, so I experimented with camera angles, and this is about the best I can do right now. So this is a closer look at the PCB that's on top of the battery. This is the battery management system. And all it is a printed circuit board that's on top of the battery pack. And it's soldered directly to the batteries. So here we have the battery main positive. It's these three terminals here. They're all the same. They just have three terminals. I guess for good connectivity. And then over here you have your negative. Probably going to have to re-record this. Having a problem getting the camera to focus. But I'm just going to do a quick overview of the different parts on a typical BMS. They're not all the same, but this is a pretty good example. So on the top you have a PCB. It's just a printed circuit board. And that's put directly on top of the battery pack. Here you have your positive, which is attached 3 times for more current, I guess. And this is your negative right here. And you'll see a lot of wires. Now this plug here I added myself, so you can just ignore that. That's a balance plug. And that didn't come with it. So I guess we can start with the main connections. So you have these really large wires. Usually the big wires, this is for pulling power out of the pack, and that's what this is. And you may not be able to see on the camera, but if you look right here, there's a row of these little fuses here. These are tiny surface mount fuses. And you'll see there's a square or rectangle on the PCB. And that's because it's completely separate from this rectangular area here, which has got 3 fuses, and this is another way to pull power from the pack. So this pack has 2 discharge leads. And boy, that really doesn't focus. I may try to re-record this later, but I'm just going to go ahead and do what I can. It's just a cell phone camera. So you can see that the positive is right here, and then you have a direct connection through these fuses. So there's no switching going on the positive side. It's happening over here. So over here you see a row of black blocks here. And I'm going to try to zoom in later. So right now I'm just going to do an overview. I'll try to zoom in later. So these are all the MOSFETs that are all in parallel. And they're all lined up here. You can see a whole row of them. And those are the main cutout for the pack. So if anything goes wrong, what's supposed to happen is this little brain that's on here, little computer chip, is going to deactivate these MOSFETs. There's a little slightly better view. And you can see there's a whole row of them, and they're all lined up. Now, as far as I can tell, there's no separate disconnect for the different outputs. It's all or nothing, so it turns everything off. So as you can see, this negative here and this negative here are all the same. They're not separated. So when these MOSFETs disconnect, then everything is killed in the pack. There's no power supplied at all. Now what I like about this BMS is, number one is it's always on. So this type of BMS is always putting out power on these large wires here. It's always on. And over here, I like the fact they put all these ceramic fuses. These are, I can't read the current rating on them. Actually, I can. I think it's 15 amps. So this one would be 45 amps, and then this would be, that's over 100 amps. Yeah, it's like 105 amps. Wow, that's hard to believe, but that's, yeah. So that's pretty impressive. Um, I would not have thought they would expect this pack to put out 105 amps. It's way overkill. There's no way that would ever happen. But that is a last resort. So what I like about this BMS is, as a last resort, they put these ceramic fuses in, and that's very impressive. I think that's going over, above, and beyond. So it's really hard to see this blurry camera and all these wires, but there's a few more interesting parts of this board. And over here you can see NTC right here, negative temperature coefficient. Let's see if I can get a better view of that. Yeah, it's not too easy to see. And that is actually a thermocouple to detect temperature. So this BMS is actually pretty advanced, and it can also sense the temperature of the cells. And or it passes that up through, I believe, this wire here. And so the actual solar generator would know what the temperature of the battery is. Or it could be both. Over here we have a small integrated circuit. And that's, I haven't looked that up, but I believe that's basically the brain, the computer brain for this BMS. And here's something you see a lot of times on a BMS. If I can just get the wires out of the way, you'll see here, you see 3 large resistors. What those are is shunt resistors. And those are used to bleed each cell group. So there's 3 cells in series, and you have the ability to balance the cells. So as the cells are charging up, one of them might be a little bit too high, and if it goes a little bit too high, one of these resistors will be placed across that one terminal, or that one cell group, to pull the voltage down, and thereby hopefully over time balancing the pack out so it arrives at 100% more or less at the same time. That's the theory anyway. It doesn't always work that way. This pack is unusual from what I've seen in that it also has a dedicated charge port. So that's for charging. This is your positive and negative. They double them up for current handling. I think that's a poly fuse, and it goes right into here, and there's a MOSFET or something right here. And it looks like that it expects to be charged through here, so that if anything happens, anything goes wrong with the charging, it will just cut the charge off. So that's a overview of what a BMS does. Now, they don't all have exactly the same features. Over here, you'll see a row of resistors. Well, that's really blurry, but I just can't get the camera to focus. So what these are, this is a row of resistors placed in parallel. They're low value. And this is for sensing current. And it's sensed on the negative side. And this is how it detects how much current is flowing out of the pack. And you can actually see the shunt. There's some thin tracks on the PCB coming over here to this chip. So obviously that's where it's using this to measure the current by sensing the amount of voltage drop over these resistors, which will be very tiny. It doesn't drop hardly any at all, but it's enough to measure how much current or amperage is flowing through. Here's a second attempt at filming the PCB. I used the zoom feature on the camera. I think it's digital zoom though, so it's probably going to have horrendous resolution. But I'm just experimenting to see how it looks. This is the kind of footage I was really wanting, but at a higher resolution. So I have another camera coming in the mail. I don't know if it'll be able to do this better or not. We'll see. But you can see now finally, well, sort of, the shunt resistors. In fact, I think these are 20 ohm. Now these are, you see there's a path for each one, and that's because each one of these resistors is for a particular cell group and is only connected across that cell group if it goes too high. Usually it's 4.2 volts is when they start bouncing. I personally don't like that because they always go over 4.2 volts. I've never seen a system that didn't overshoot the voltage. They really should start at 4.19 and hold it there. You know, try to stay outside the margin of error. And the difference in the cell being filled up, or I should say the difference in cell capacity would not be very much. And then the cells would probably last longer because you're not overcharging them. Here you can see the ceramic fuses. I believe this is 105 amps. They're 15 amps each. This is 45 amps. That's a lot of current. But these are a last resort. These normally would not blow. That's why I like this BMS. It's designed in such a way there's multiple protections. And I think this yellow thing here is a polyfuse right here. I haven't looked it up. Not going to look it up. Some kind of polyfuse or circuit breaker or something, I'm guessing, is what that is. It might be 16 amps. I'm not sure. And I think that's to cut off the charging if it goes over a certain amount. And here you can see the negative, the NTC, the thermocouples right there. Those two black wires. That's for sensing the cell temp. So this footage is a little better. You still can't read these chips though. I'm not even going to bother. My eyes can't handle it. I don't have a microscope. There's another little chip right there. Now, I don't know. These are obviously the two biggest ICs on the board here. So they probably handle pretty much everything. Who knows what that is? But obviously that's where the intelligence of the circuit is. And over here, you can see the board is marked 3.7 volts right there. And this is your first cell group, well, depending on what direction you're coming from. Let's see. Yeah, actually it is. So coming from the negative side, this would be 3.7 volts, so you should get about 3.7 volts here. And that's put there for technicians who want to monitor or check the battery with a multimeter. And over here, you have 7.4 volts in the upper left-hand corner. I use the multimeter probe. Right there, it says 7.4 volts. So this would be your 7.4 volts right here. So these 2 points are the middle of the pack. And you can see I have this balance plug connected. You can see the first wire goes to the negative. This goes to the first 3.7 volts. This goes to 7.4 volts. And this goes to 12.6 volts or 11.1 volts, whatever you want to call it. And I added this on later just so I can keep an eye on the battery since it's going to be in storage. Then over here, yeah, this is much better footage. If it was just higher resolution, I'd be happy with it. Over here, you can see these are the MOSFETs. And then over here, there's the shunt resistors for measuring current. And these are in series with the output. And they're all, but the resistors themselves are in parallel. They're 5 ohms, I think. So that makes a 1 ohm resistor, although I'm just guessing at that. I believe those are 5 ohm resistors, but now there's probably nothing on the bottom of this board. It's just flat. So that's a look at a BMS, a closer look, and you'll see all sorts of things, all sorts of variations, just like this board. I mean, not just exactly like it, but it'll kind of have this look. It'll have similar connections, but you have to be careful because not all of them are wired up the same way. It can be very confusing. There's a ton of wires. I mean, look at all the wires on this battery pack. It's not too easy if you just are seeing this for the first time. It may take a while to figure out what does what. But in general, BMS is there to act as a gateway between the user of the battery and the battery itself, and to protect it from harm, overcharging, over discharging, over current, and over and under voltage of each individual cell. So a pack like this should be monitoring each individual cell, and if any one cell goes too low or too high, depending on how it's programmed, it will just shut everything down. What that will do is protect these cells from damage. And that is the purpose of a BMS. Balancing, to me, balancing is secondary. The most important part of a battery management system would be to protect your expensive cells from being destroyed. So if one cell goes way too high, it should just shut everything down. Not all BMSs have balancing. This one most clearly does because you can see the shunt resistors right here. So obviously it has some kind of balancing functionality built in. So that's an overview of a BMS. It's not a really deep video, not a really deep dive into it, but really there's not a lot on here. The most mysterious thing on here is these integrated circuits, which if you look them up, a lot of times they're just an off-the-shelf component, and there's a reference design, you can look that up, and it'll tell you how to hook it up and different things you can do with it, and whether it's programmable or you can change the settings, things like that. This other little chip here does have text on it, but my eyes ache so bad right now, there's no way I'm going to try to stare at that. It doesn't really matter. What's important for the layman, for the average Joe, is I just want to make sure I understand how to troubleshoot something like this. If I see something like this in a device, I don't want to be intimidated by it. I want to know enough about it so that I can determine, hey, is this worth scrapping? Is this worth buying? I may not have a lot of time. And I know that when I get a pack like this, the first thing I'm going to do is check the voltage of the overall pack. If it's in the 11 volt range, 10 to 11 volt range, surely the batteries aren't completely run flat because there's only 3. This is a 3-cell system, and I expect around 10 or 11 volts or more. And if I see that, I know all the cells have to be at a decent voltage. However, if I saw something like 6 volts, that's a problem. I would know right away that pack had been over discharged and I don't really want it, or I'm going to have a problem. Maybe I'll have to tear it all apart and just get a few good cells out. So that's the end of this video. I tried to keep it from getting too long. It's not meant to be a really deep video, just an overview. I do intend to make more videos on this topic later as I learn more. And I am interested in acquiring a number of these packs for various projects that I have in planning. I don't know when those projects will actually happen. I need a few things to move out of the way first. But this will get me started. And it also, some people don't want to listen to a 60-minute long video about a battery pack or battery packs. So this one kind of fills the gap. I hope you found this video helpful or informative in some way, or at least slightly entertaining. Thank you for watching, and I'll see you later.